just wanted to double. Oh, there. Okay, great. Welcome, everybody, to our February meeting of the 3DHP for the Nation Monthly Forum. We're fortunate today to have Dave Blodgett with us. He's going to be talking about the conceptual model and Mainstems logical data model for the 3D hydrography program. Before we get to Dave, a little bit of housekeeping. As you all know, this is a cooperative agreement with USGS, and our primary goal here is to engage state and local governments and private sector partners in project activities. So very glad to see you all here today. Just wanted to give you a brief update on what's going on. Mapping this to our task is if there, first we have a 3DHP monthly forum, which you know because you're here. All of the reportings, PowerPoints, Q&A docs are available from the NHDPlusHR learning link. I'll put that link in the chat in just a second. I did want to let you know that the Minnesota culvert mapping Q&A doc and presentation and recording are all available at the learning link now. You just go to the learning link and then go to 3D hydrography. This does require login, and you should have that if you've registered with the site, as you have to be at this meeting. Second task is to establish communities at mynhdic.org, and all of you are aware of the 3DHP for the Nation interest group, and the January 23rd interest group meeting notes. The recording from the meeting is now available on the learning link. We inventory state and regional experiences. We're maintaining the inventory. You'll see there was a short form and a long form. And other activities, prioritizing critical factors, developing guidance documents, and compiling best practices. And our current activity is culvert mapping activities and attribute survey. And I'm going to go ahead and apologize for putting all of these. You've gotten multiple emails on this, and let me just explain what's going on here. We are putting a survey up, and it will stay up. But our primary objective is to get some inputs in preparation for the mid-year meeting. So we need to get some general guidance, just some general ideas. In particular, USGS is actively looking at a minimal set of attributes for culverts. And so any input you can get to us by Friday is greatly appreciated. That'll enable us to put together some discussion points for the NHDPlusHR mid-year meeting. A link to the survey is in the chat, along with a few other things. So thank you all for that. And then finally, we of course have the NHDPlusHR 3DHP Info Hub. All of the resources I've listed are available from the hub. That link is also in the chat. Please check it out. And always we provide 3DHP program feedback. With that said, I am very glad today to introduce Dave Blodgett, who is a research engineer with the USGS Water Mission Area. However, Dave, I believe you're on detail to 3DHP working on the data model. Is that correct?
That's correct. Yep.
And you are free to share your slides.
All right.
Really appreciate having Dave here today. I know there's been a lot of questions about the data model, you know, all of it's coming from a NHD perspective. So thank you.
Yeah, thank you for having me. And yeah, like you said, I'm Dave Blodgett. I sit organizationally in the Water Mission Area within an integrated modeling and prediction division, geospatial intelligence branch. I've been with the survey for 12, 13 years or so now, and a few years ago moved into the kind of research engineering career track called EDGE. So I have a lot of opportunities to kind of help with engineering design across the USGS water space, but also beyond. Now in the National Geospatial Program, Technical Operations Center. I worked for a little time. I worked down at the National Water Center on the next phase of the National Water Model. And I've been working in kind of standards development in the interest of things like the National Water Census for a number of years now. So when the opportunity to help out with the data modeling activities going on around the 3D hydrography program came up, it was a good opportunity, and this is a really exciting thing to be part of. I'm super excited to be able to help shepherd this whole thing forward and grasp the value that is the NHD and try to bring it into the next phase. So this talk is going to be a little different than probably most to this audience, but I hope it's illuminating. I hope I can leave you with some ideas and some questions that you might want to follow up on and go, learn essentially a little bit more about where all this is coming and going. This is thinking pretty generally, pretty conceptually, but please bear with me. I'm going to do everything I can to make it approachable and interesting. So I want to start here, and this is a slide I built out quite a while ago for an AWRA geospatial technology conference. And if you haven't heard of it, there's an XKCD comic adjacent thing called the Upgoer Challenge, which is to use the top 100 words in the English language, which thousand is not one of the top 100 words. So you have to use the top 100 words to describe a complex technical topic that you're very familiar with. And so I wrote an Upgoer challenge for this data standard called high features, surface hydrologic features concepts. And I want to start there because I think it's a provocative piece. So here it goes. I helped build a good way to explain how we understand the things in the world that catch water from the sky and, following in the down direction, group that water into bigger and bigger groups. We call those groups water bodies. The water catching things and their water bodies join, and the water in them moves in the down direction, eventually getting to the deep blue water body. Although we think of a water catching thing as a single thing, we also think of the water catching thing as different kinds of parts that work together and form a whole. Some of the kinds of parts we decided to put in the good way to explain water catching things are its outer edge, the line water follows from its top to its bottom, what its inside area is like, all its water bodies together, and the water catching things that go with each of its water bodies. Each of these different kinds of parts is an important and special part of the explanation of what a water catching thing is. Together, they form the whole way to explain the water catching thing. Okay, so that was overly simplified terminology for this idea of a catchment, a water catching thing. And that a catchment is conceptually actually multiple perspectives of, it has multiple perspectives. It has an area, it has a divide, it has a flow path, it has a surface network. It has a network of smaller catchments that you could delineate within the single larger catchment. And each of these is kind of a partial representation. It's a partial conceptual representation of this idea that we all kind of understand of catchment. And so that's the basic notion that's put forward conceptually. That's the basic conceptual framework for this standard high features that has now been published for a few years in the Open Geospatial Consortium space and is responsive to some needs that was put forward by the World Meteorological Organization's Commission for Hydrology. So we're going to dig into what that means a little bit, or what that is in terms of a informatics tool. Okay. And I want to start here. This is really basic informatics ideas. So high features and the data modeling that's going into the 3DHP data model uses two sorts of problem decomposition or problem domain decomposition. It uses a spatial domain decomposition, which obviously, breaking things up by space, hydrologic units, catchments, et cetera. And it uses this conceptual kind of model concept of domain decomposition by saying, like, look, we can have catchment polygons that have flow paths that join their inlet to outlet. The flow path is kind of conceptually separate from the divide, the polygon, and there's more. Like there's a conceptually distinct set of water bodies that link to those flow paths, and there's a conceptually separate set of hydrolocations that link external information into those flow paths. And if we use this spatial and this conceptual decomposition carefully, we have a nice set of building blocks, right? And so the other piece of jargon, or the other kind of conceptual thing that I want to be very clear about, is when we talk about features in this context, we mean features that have a certain class in the kind of object-oriented programming sense. So a class is a thing that it's a set or category of things having some property or attribute in common and differentiated from others by kind, type, or quality. And this idea of class is really important because treating things generically as features that have a certain class allows us to apply that same concept, that same logic in multiple technical settings, whether it's in a SQL database or a shapefile or a web mapper or whatever it is. We can talk about having features of the same class as having similar characteristics, kind, type, or quality, right? And that's really important to this data modeling exercise. So these are just two really important. This idea of spatial and model domain decomposition and this notion of class are really important kind of parts of how we are thinking about the data model. Okay, so I have a 5-year-old and a 2-year-old, and so when we graduated from Duplo to Lego, we made this crazy realization that Duplo is actually a superset of Lego in a very strict way, actually, because you can use Legos and Duplos together. The Duplo is just 2 Lego studs wide. So the system fits. It's actually a multi-scale system. And I use this as an example because everything we do, practically speaking, fits into some quote unquote system. A very simple building blocks that allow us to create complex arrangements, right? And so what are the building blocks that we work with in geospatial information? Well, in the case of hydrography, we use a core abstraction, which is this idea of features. Features are an abstract representation of real-world phenomena. And we also use this idea of referencing by coordinates, right? Our features form geometries that have coordinates. Using those two notions, those two core concepts, we construct incredibly complicated feature data sets with all kinds of attributes and geometric representations and all this stuff. But down deep, it's a system of this idea that a feature is an abstraction of a real world phenomena that has attributes, and we represent its geometric attributes with coordinates, right? So I just kind of want to draw attention that we already have a system we use, whether we recognize its fundamental components or not in those cases. But there's more to the system. There's more nuances to the system, and especially in IT design, there's a pattern that people use of reusing building blocks to solve specific domain problems. When we talk about domains, like domains of discourse, domains of science, domains of knowledge, right? So you have a use case that's defined within a given domain, and you apply a set of engineering tools. You apply a set of capabilities to that use case in what we would call a domain engineering process. And that's what we're doing here. We're trying to use pre-existing tools, general tools, to satisfy problems defined in the hydroscience, hydrology, hydrography domain, right? And to do that, we have some some more or less domain specific data models or building blocks, conceptual logical building blocks. One of them is this data model called observations and measurements, which is kind of rooted in physics in a lot of ways. It basically says that we use some methods to make observations or make predictions of a thing in the world, a thing that we recognize to be a thing, a feature. I'll come over here so you can see my mouse. So yeah, we use methods to make observations and predictions. They're usually of a feature, some real world entity that we recognize, and the information that comes out of that observation is some kind of result. It's the time series of stream flow, right? That the river is the feature, the time series data is the result, the method is a pressure transducer with a rating curve, and the observation is the metadata about that system of information that needs to be all in scope to provide a complete kind of understanding of what's going on. So the feature thing is what we really want to talk about here, and that's what's on the right here. This is the catchment. This is the core kind of catchment data model, where we have this idea of a catchment interacting with a nexus. So this is like the node in NHD plus, and the idea that a catchment can have multiple realizations. You could have a divide, you could have a flow path, you could have an area, you could have a network of catchments. And then this idea of aggregation is really fundamental, right? You have the ability to say, well, this catchment actually is an aggregate of catchments. So you have, say, a 8-digit huck with a system of 12-digit hucks inside it. And the ability to do aggregation follows some rules around things being either dendritic or not diverted outside of the basin boundary, or interior flowing within itself, right? So this is the basic kind of nesting and network relationships for this top level conceptual feature that we call a catchment. And it fits into this paradigm of features, observations, and predictions, and we implement it using this idea of domain engineering, where we're taking these domain-specific data models and finding general tools to satisfy the use cases. So one other layer of kind of design methodology to add to the mix here is this idea that we typically design systems starting at concepts, where we kind of think about what's possible, the highest level of generality. We move into logic. We say, well, this is the reality that we are going to model. These are the assumptions we're going to make. These are the concepts we care about for this particular case, that kind of thing. Then the physical is, no, we're going to use that particular software. We're going to write a schema using that technology. We're going to implement it in that whatever database backend, this kind of thing. And I'm mostly talking about conceptual here, and a little bit of what I'm going to talk about is logical. The physical for this process is intended to be flexible. We want to be able to implement these concepts and this logic in multiple technologies. So the physical implementation is actually something you would take on in an implementation project, not a design project necessarily. And not to say that you couldn't do implementation as part of a design project. I'm just kind of drawing a firm distinction between design and requirements, kind of thinking about requirements at this higher level, and specific implementations with performance characteristics and integrations and et cetera, et cetera, et cetera. So, okay, so we can apply these governing models to multiple disciplines information, and we could wander off in all kinds of wonderful directions. But here I'm going to focus in on the stream gauge river surface hydrology use case, and lakes are a tightly bound component of stream gauges and rivers, and there's a lot of, so lakes are kind of implicitly included here, but there's a separate set of conceptual thinking around groundwater that's not unrelated to this, but is from a separation of concerns, conceptual separation of concerns is separate for now. And so in the in the kind of international standards space, there's the hydrology domain working group of the Open Geospatial Consortium, started by a coalition of primarily national government organizations like the USGS from around the world to start to roll out a system of standards to support information in the hydrology domain. And so what we're talking about today is WaterML2 Part 3, surface hydrology features, where WaterML2 Part 1 is fairly broadly adopted. It's a standard for sharing and disseminating time series information. The second one is ratings, gaugings, and sections. So this is the typical pattern for stream gauging is you go out and measure stream flow at a given stage. You measure stage, you apply a rating curve, you apply a mapping from stage to discharge. And so this ratings, gauges, and sections is the information that is that discharge translation rating curve. Then we get surface hydrology features, groundwater features. These two exist as full standards. Water quality observations is actually currently a best practice that layers some common implementation patterns on top of other standards. There's an ongoing interoperability experiment to establish more formal standardization around water quality. And we have a fair amount of thought in the community of this Open Geospatial Consortium community about where we want to go with things like cross sections, river networks, channel geometry, kind of extensions and implementations of groundwater information, and so on and so forth. So this kind of forms a system of discrete but interrelated standards, and that's something that is changing over time. You know, this slide is from 2016, and I guess the other point I want to make here is that this stuff moves slowly, necessarily. We're trying to get it right and have it be durable and not necessarily have to be reworked on a regular basis. So let's think about what is going on in a river when we think about observation. So this observations and measurements standard. In this particular graphic, we have two observations ongoing and one feature of interest. There's a stream gauge, there's a grab sample. So those are two different observation acts that are ongoing and one feature of interest, this river. In high features terms, we have a hydrometric feature that's a hydrologic location along this river. We have a hydrolocation of this sampling procedure. We have a water body that is a river, right? And these are kind of the classes. This is when I was saying, you know, class is really important here. These are classes of information. And so we would expect the hydrometric feature to have a certain set of information. A hydrolocation is going to have another set of information. A water body of type river is going to have another set of information. So what are the core classes that we're talking about here? This is a graphical kind of depiction of these core classes of high features. And this speaks to the modeling concept domain decomposition that we're using. So I start with the catchment area. And this is the actual hydrologic landscape. This is the land that is where soil hydrology takes place, essentially, or overland flow takes place. It's not the boundary, it's not the polygon, it's the actual interior, it's the characteristics of the interior. And so you could think of this as the unit that actually calculates a water budget for a piece of the landscape. And by that token, how we realize or represent the interior of a catchment is totally flexible. There's lots of ways that people do it. It's a grid, it's a set of parameters, it's a elevation surface, it's a there's all kinds of different ways you could represent this catchment area. The second one is this idea of a flow path. So this is the linear feature. It is not a water body. It is a path through the landscape that is recognized to be the path that water would follow in a very idealized sense from an inlet of a catchment to the outlet of a catchment. And so this is what we do linear referencing on. And when we say a hydrolocation, we mean a point that can be thought to be along a flow path. It doesn't have to be physically co-located with a geometric representation of the flow path, but it's got to be close enough that you could establish that if you had a representation of the flow path handy. And that's a tricky thing to wrap your head around, but it's really super key to what we're talking about here. We can say that a stream gauge is a hydrolocation. It's on the bank of a river that's very wide, and if you have a 1D representation of that river, the stream gauge on the bank is not on the flow path. The stream gauge on the bank is on the bank, but it's measuring flow for the entire watershed upstream. And so by that token, it's on the flow path of the entire watershed upstream. And that physical disconnect, I guess, that we all kind of use in hydrologic concepts is not well supported in the precision of referencing by coordinates. And that's part of the kind of conceptual backbending we do in hydrology. Is a lot of things are more fuzzy than the precise geometry that we have in our features. So anyway, that's a bit of an aside, but this flow path concept is super duper important because it gives us a linearization of a river that we can do linear referencing on. But then there's water bodies, and water bodies are separate. They're the thing that you would do hydrodynamic kind of characterization with. That this is where you would have water quality characteristics. You do mixing. You do flood inundation. You do these are the water that sits on top of the landscape. And then there's this notion of catchment and nexus that kind of encompasses all of that. A catchment is a holistic feature, and this is I'm constantly tripping over this because in NHD plus, catchment is the polygon feature, but in the high features conceptual space, catchment is a holistic feature that includes. I shouldn't say includes. A catchment is represented by multiple features that are partial representations of a catchment. So a catchment boundary is a partial representation of catchment. A flow path is a partial representation of catchment, etc. And a nexus is the same thing. Typically, a nexus is going to be thought of, idealized as a point along a flow path, in the sense that there's an outlet, there's an inlet to a given catchment. The inlet and outlet are nexuses. But there's other types of nexuses that we're having to recognize. And so in particular, coastal boundaries. When you have a catchment that has no discernible flow lines in it that goes to the coast, its outlet, its nexus is actually a line or a boundary with a water body. It's not just one. It can't be thought of as just one point along a flow path because there's no flow path. And in the same way, a catchment around a playa or a catchment around a kettle lake or a prairie pothole, there isn't just one outlet to that thing. It's diffuse outflow into groundwater or diffuse outflow into the atmosphere from a lake. And we need to have some more complex representation of its outlet, basically. So, but the nexus concept is still the nexus concept. A catchment has an outlet, right? And last but absolutely not least is the hydrolocation. It's just a dot, and that's not a fly on your screen, that's a dot. It's a location on a flow path that can be linked to other features. And that's the key, is hydrolocation provides the linking mechanism to cross scales, to link to outside data sets, to add attributes that change along a river, et cetera, et cetera, et cetera. So this is the pictorial, the pictorial, I don't know if that's a word. But anyways, this is the set of cartoonish graphics that I've cooked up to represent these concepts. But there's quite a bit more. There's a whole set of features around surface hydro features, so water bodies, and there's more in a kind of hydro feature package of the data model that gets into a lot more detail about this idea of partial representation of catchments and how the partial representations can be formed in networks and all this. So, but this is a good intro and really gives you a sense for the core components of high features. So this all explodes out into the same diagram, right? You've got there's a hydrologic location that is thought of as a point along a flow path. So flow path here. You might have a cross section that is at the same, that's thought to be at the same linear hydrolocation, but is a line that describes bathymetry. That's characterizing a channel. The channel contains the water body. And this is, I could have marked this diagram up even further with additional feature types that we kind of recognize exist in this setting, but don't necessarily hold in every data set. And they might all be kind of pinned to this same hydrolocation, right? And that's really the key, is if we can recognize this flow path feature in multiple data sets, or have hydrolocations kind of cross-reference the same set of flow path features, then our data sets can kind of start to hold together across kind of hydrologic integrations. That's a little bit of foreshadowing what I'm going to talk about next, but I want to further drive the high features points just a little bit with a different example. So this is a map of Black Earth Creek, just west of Madison, Wisconsin. And so there's these valleys that are full of glacial outwash material, and there's a number of disconnected flow lines. You can see these kind of, they end in polygons, which I believe are coded as swamp marsh, but they're actually just kind of wet field areas where the water goes into the glacial till. And these aren't actually, anyways, I don't want to get into too much detail. These aren't actually disconnected. They flow through subsurface, near surface gravels, and do find their way into rivers. And but what's shown on this diagram is in black a catchment divide. The hydro network of flow paths is in blue. There are some water bodies in light blue. What we're not showing is the nexus or hydrolocations, or a hydrographic network, where the hydrographic network is the network of water bodies. The hydro network is the network of flow paths. And there's lots of other things that aren't shown, but the core features are shown here. And so here I've zoomed in to the very outlet. So we're zooming way in here, right? And in pink, I have added a width to the flow line features. These are the same blue flow line features, but because we've zoomed in, their nominal width is much narrower. The pink line here is the same nominal width as the blue line here. And I'm just kind of using this to make the point of it. There is a distinction between a representation of water bodies and how wide water bodies are, and the path that connects an inlet to an outlet. And so the blue one-dimensional line that has some nominal pen width in this visualization is just a path. The pink could be thought of as a representation of a water body because it now has a width that's explicit. It's a polygon, right? And the other thing to point out here is that the nexus idea is not necessarily a confluence. So the nexus for this, the outlet of this black catchment, the black polygon boundary catchment, is actually down here just below the last confluence within its network of flow paths. And that's just a side point that's very important to realize, that this nexus feature is not necessarily a confluence. It can be any location on the network where you want to basically say, here's where my outlet is. Okay, so what does all this mean for the NHD and beyond, right? And I come back to this, like, is the NHD of my own creation Lego that we're building out of these components? Maybe, kind of. If you're not a Lego person, this tradition of mocks or MOCs, my own creations, it's pretty amazing. The Lego mock YouTube. If you don't have a 5-year-old and don't go on YouTube to look at Lego very often, you should consider it. It's pretty cool. Very peaceful to watch people put together these crazy Lego creations with quiet music, which is what people do on YouTube these days, I guess. But the concepts I just ran through, in the same way that a collection of Lego bits provides a system that's kind of a well-separated set of components to build a Lego creation, they provide the well-separated components to build a hydrographic data set, right? And we're using them for the 3D hydrography program data model. And so at the core of this data model, we have the flow path realization of catchments, so this linearization of the flow lines, or the linearization of the flow line network that corresponds to catchments. The catchment divide realization of catchments, so we'll be creating catchment polygons for the flow path realization. Water bodies linked to the network via this main stem concept that I'm going to talk about the rest of the talk. And then lots of hydrolocations that are also linked to the network via this main stem identifier. Okay, so what is the main stem identifier? Well, if you want to read more, there's a couple of resources. The first is this paper, Mainstems, a logical data model implementation in environmental modeling and software. If you just Google Mainstems logical data model, you'll find it. It's a nice piece of work. I'm really it took a good chunk of time to get it out the door and get it right, but it's a really nice piece of work, and it's a good introduction to what this encompasses. And these two graphics were generated in the work that led up to this manuscript. One is essentially the main stem one at a time animating in network for the country, just kind of illustrating what a main stem is. So each of the features that's animating in is a main stem. And this animation could keep going and going and going until the whole screen was blue, because the main stem concept crosses scale. A main stem can be defined at any scale, and it kind of has to be. The other thing that's here is the fact I wanted to understand how well connected the watershed boundary dataset HUC12 network was. So I built an animation, and I kind of thought it would be cool to have it all converge at the coast. So you can see it's all kind of timed so that it converges at the coast. And this was part of writing software that could link the HUC12 network to the river network, right? And the attribute that I used to establish this linkage is this main stem, and it's an identifier. It's an identifier for each one of these paths. So I'm actually just going to read this. By defining main stem flow paths and identifying them across data sets, the sophistication of incremental catchment data models can be handled simultaneously with a persistent and minimal network of main stem flow paths connecting headwater and outlet locations. So that's the crux of it. We have this incremental catchment data model that covers the landscape with these features that are connected. And it gets really complicated really fast. And it kind of starts to eat our lunch when it comes to data maintenance and integration and all the tools you need to work with it properly. And to make some of those problems easier, because they're not all going to be, it's not possible to make a lot of them easy. A lot of them are just complicated. We need something really simple to underpin all of this. And that's this data model. And so what are the defining features of a main stem? First, the headwater area. And we identify a headwater area in various ways, but the key is there's some river that comes out of this headwater area that we kind of recognize to be the start of a river that drains some headwater region. And there's lots of ways that can happen. Topic of study that we need to dig into more. Then there's a path that connects that headwater region to some outlet, right? That's a main stem. You have an identifier of some kind for a headwater. You have a network that gets you to another identifier, which you think of as the outlet. And so if you have a headwater identifier and an outlet identifier and the data set that those identifiers came from, you can retrieve the path that connects you between the two, and that's the main stem, right? And what's really, so coming back to this idea of crossing scale, what's really cool about this is if you combine this idea of main stem with the notion of incremental catchments or hydrologic units, as you zoom in, you cover the whole map, you cover the whole landscape with catchments, the incremental catchments that correspond to the little pieces of the main stems in between each of their confluences. And so this is it. This is the main stems data model. It's this ability to have a network that holds together across scale and is integrated with catchments. So that's the underpinning concept. And I'm actually just going to make a couple more comments at this point. The same underpinning concept is in NHD+. It's already there. It's the level path. And the ability to assemble drainage basins based on the network of attributes in NHD+ is really what we're recognizing here. But we're pulling a couple of those attributes out and turning them into persistent identifiers. We're pulling them out and using them in a different way. So the reason I'm so excited about this, or the reason I feel so confident that this is reasonable, is that this is really tried and true. Since NHD, really since even RF1 days, some of these concepts were floating around. But all the way through NHD+, V1, V2, HR, this core network arrangement has been the way that we've dealt with these networks. It's the way we've worked with the networks. But we've had an identifier for features that was at a finer grain, finer granularity. And so going forward, what we're saying is the top level identifier is now the main stem, not the reach code, basically. That's the big shift. And it basically, it limits the number of feature identifiers that we need to maintain and gives us a cross-scale arrangement and a way to kind of have more priority over what needs to be super durable and what can we tolerate some evolution and change on. Those kinds of things are much easier to deal with. On and on and on. I'm happy to talk about the strategy more. But so then let's talk about 3D for a second. The 3D Hydrography Program is sponsoring this evolution of the process being implemented by folks within the National Geospatial Technical Operations Center. And this diagram is one I laid out early in my work, and I've kind of evolved it as we've worked through some of the nuances that talks about how this is going to fit together at a 30,000 foot view. And so the way I just walk folks through this, we've got over here on the left, elevation derived hydrography is the source of new information. This scaffolding nodes and main stem network is, think of this really as scaffolding that is instrumental to building the data set, right? We have a set of nodes that basically need to be at the boundaries of an elevation derived hydrography collection, so we can fit that collection into the prior network, the pre-existing network. And then we have this main stems network, which is the pre-existing identifiers, which need to be conflated onto the elevation derived hydrography. The nice bit is we don't necessarily need the geometry of the primary path to be the same. We just need to connect the same headwater to the same outlet. And so the conflation process for main stems is a little more of an achievable, a little easier to grok, I guess, than conflating line to line kinds of evolution. And so those two pieces of information come into ingest and pre-processing. Noting that the very first time we do this, the 24K NHD will be at the table, will be in play as part of the main stems network scaffolding nodes. And we're working through that kind of pre-population of the data with the existing 24K network right now. But just noting that the initial Mainstems network is going to be populated from the 24K NHD, so that we have the reach codes and things like that will come forward into the rest of this on day one. So then the production process, which is really going to be out of public view, but there's plenty of awareness of what's happening, or needs to be plenty of awareness of what's happening, starts with an ingest and pre-process step where we actually do conflation and add network topology, identify primary upstream, primary downstream, make sure Mainstems are represented appropriately, or vetted and changed if they need to change. We find errors, those kinds of things happen. Then we go into catchment delineation. We go into aggregation, kind of a network attributes. So this is where aggregation being, there are going to be some very, very, very short flow lines in this data, and we probably aren't going to create catchments for all of them. So aggregation of the initial set of catchments is probably going to be a service to everyone. So exactly the logic for how small or how big catchments are going to end up in these outputs, that's a large, I shouldn't say largely TBD, but that's a design process that we need to continue to think through as we get into working this process. And then finally, post-processing and regression testing is really just to make sure we didn't miss anything. The regression testing piece is also super duper important for basically maintaining continuity in these Mainstem identifiers, and making sure that we're not kind of breaking interoperability with data sets that we don't need to work with the data. And then from there, we export to views, and the views are essentially the versions of the data that we can build data products off of. A version of the production data that is suited to the needs of people who are doing cartography with NHD, a view of the data that's suited to the HydroAdd linear referencing tool and other linear referencing applications where people need to figure out where stuff is along the network. And then the last one is this HydroFabric, which is really kind of the NHD plus view, if you want to think about it that way. This is the thing that modelers could take and build modeling frameworks off of. So those are the three views, and each of these would have specific data services or specific data products built off of it. And that's further over on the right, and additional design work that gives us the ability to create information products that are very similar probably to the data products that are out there now, or look, feel, function, et cetera, very similar to the current data products. So that's essentially the talk. Just kind of reiterate the core data model of flow paths, catchments, water bodies, hydrolocations. Mainstem identifiers provide a cross-scale persistent identifier scheme. And when not persistent, at least simple enough that maintaining it becomes a realistic prospect, or a more achievable prospect than has been historically. One detail I would add here is, if you're familiar with the reach code and flow line, where there's multiple flow lines for a given reach, exactly how the flow path relates to individual geometries is a bit open to discussion still. There's a very good chance that there will be a quote unquote flow line feature, and a catchment will be delineated around some one-to-many set of flow lines. And a flow path will be a slightly higher level feature. So that would basically mean that we might have something that is akin to NHD Plus version 200K or so catchment size, but within that, there's many, many more individual flow line features that didn't get catchments, but nevertheless, there's a network that's at a much finer resolution. I think that's where it will land, but we have a lot of open questions and conversation about what the appropriate scale for creation of catchments is, and the appropriate scale for distribution of catchments is. And because we're starting with the EDH process, we have the ability to honestly, we had the ability to iterate on this a little bit and figure out what the right solution is, and find out where, where does software start breaking versus how big is too big for some people's applications. What's the happy medium? I bring that up because it's one of the things that I think is one of the more important. It's one of the more important areas for us to get feedback about in the near future. So, so that is what I have. From there, it's open to questions.
Thank you, Dave. Sorry, took me a while to get off mute. Very interesting. A little above my understanding, but I think we've got some folks on the line who are with you. I'm seeing some good comments about great explanation of the process. I'm asking folks to go ahead and pop some questions into the chat, and we'll capture those and let Dave respond as he's able. So please, I did, I said you had me with what was it? Water catching things. That was good.
If you haven't done an upgrade challenge, like it's a good fun. Conferences sometimes host them as a happy hour activity. They're fun.
So please, if you have questions, comments, or would like Dave to elaborate on something, okay, we've got a question from Danielle Favreau. I won't say that right, Favreau.
Yeah, that's a good question. I wouldn't say, so I use map scale just as a point of reference. I don't mean to say that there's a 100K map scale product being developed. The EDH data that gets collected will be is expected to be as fine or finer than 24K. But there is a recognition that that's too fine for a lot of people's applications, especially when we're talking about little itty bitty incremental catchments. And establishing what the right scale for catchments is an open question. There's no question that the actual flow line hydrography will be as dense as EDH implies it should be. So yeah, and that's good information. If catchments for every 10-meter long flow line are required, we need to know that. So
Thank you. Others, please. Questions, comments?
Hey, Linda, this is Sam. I was wanting to ask, is there ever an idea or a philosophy to bring in the stormwater data into the 3D-HP from like urban areas, basically connecting that network of drainage underneath the cities and all that stuff into the whole NHD?
So that's a little bit outside of the scope of my direct involvement, but the idea at this point is that 3D Hydrography Program is using elevation derived hydrography that has come in through a contracting process as its baseline information. I could certainly see a world where there was a vehicle to include below ground urban infrastructure in that kind of a contracting arrangement, but it's not in any specifications thus far.
Hey, Dave,
So
it's Steve.
Yeah.
So for Sam there, it is a longer term goal. We're starting with what we can do with elevation derived in the sort of vast swaths of the country that have LiDAR. I know you may or may not be familiar. We've done a couple pilot projects in some urban areas, have a couple more lined up to look at or what's required to map some of those urban deserts. We do have a vision to get that done, but it's not a year one problem.
Thank you.
Yeah, I'd be curious, the comment, what makes people think that the 3D HP may not meet all the needs?
No, it's just the future of 3D HP and where the whole hydrologic model of the United States is going, creating a vertically integrated, database of all the different things that affect hydrology, from climatology to river gauges to everything, so stormwater obviously is a big factor in that. So I was just kind of curious, what the longer vision is for you guys and where you're trying to go.
So I think, Dave, are you referring to Jane's question here?
Yeah, I'm curious if there's a specific, it's a pretty open-ended statement.
Yeah, Jane, would you like to elaborate on that?
I don't know that I can articulate that yet, but like what Danielle wrote, and we're creating this elevation derived hydrography to meet the needs that were articulated in the hydrography requirements and benefits study. But I don't understand this new thing enough to really even visualize what it's gonna, how it's gonna be used. Is this for a different set of users?
So that's a fair point in that, so at a very local scale, an EDH collection is not going to gain that much in many cases from having a broad integration framework on top of it. But having data that are only relevant to local applications isn't enough. And what we're trying to do with what I'm describing here is provide a high-level framework to layer on top of high-density local data that allows us to do both local applications and have a nationally integrated product. And it's daunting. It's really hard to imagine exactly how this is going to work out and play out. But from everything we're seeing with test data thus far, and the amount of work that's gone into the design of this so far, testing of everything, I hope we can achieve what we're setting out to do, and I think we can. But it's no joke that it's a challenge. So.
Al Ray, is there a role for rasters such as flow direction raster other than as a means to derive catchments? In other words, will 3D HP include a flow direction raster?
Yeah, my understanding is that the raster products that are used for the elevation derived hydrography geometry will be made available. Exactly how much hydro conditioning and post-processing, such as flow direction, gets done is still a bit open to interpretation. The specifications are actually evolving on hydro conditioning, so not entirely sure where that lands, but needless to say, yes, the elevation data will be available as part of the overall data product. So.
Bill asked, how can we define rules to define and map the upper extent of EDH flow lines, map and do it at some measure of national consistency? Yeah,
so that's an area of research that was a major topic for the NHDPlusHR and the 24K network to get a generalization filter approach that was applied as much as possible to the NHDPlusHR, and I think we do expect to have that kind of generalization capability here. And the Mainstems concept gives us something of that, and we'll be applying these kinds of attributes as we go. And I'll actually bring that back to the teams. I don't think that's been a topic, enough of a topic of discussion of visualization of this stuff across scales. But I know it's a major consideration as we get into building these data products. So like in the cartographic view of this data set, I could see adding a generalization filter attribute that would be an example of where it would fit. So.
All right, Danielle again. Many states have worked to create NHD at better than 24K and HUCs at 14 and 16 level. So far, 3DHP seems to be making coarser information, well, then better. Well, I'll let Danielle defend that, discuss that one, but any response to that?
So far, 3DHP hasn't created any data. So I'm going to hold judgment on what's going to be created. But the goal is for the elevation drive hydrography to be at a finer resolution than 24K and developed with local stakeholder involvement in the EDH collection process. So if there were local interests in certain characteristics, that's in the scope of the contracting arrangements. And hydrologic units at 14 and 16 is an interesting one. We will certainly have catchments that could be used for dendritic drainage basin creation at what you might think of as a HUC 14 and HUC 16. But the idea of hand delineating such small drainage areas feels a bit of a stretch. So the use cases where we need finer resolution hydrologic units will be supported. But exactly how those get delineated is going to be something we need to do at a more kind of nationally consistent and approachable way. That's not to say that somebody couldn't take the elevation products and the EDH and build their own catchment networks. And that's absolutely something that could be done with the expected EDH products that are going to come out of this. So,
Dave, do you want to elaborate a little bit along how local or higher resolution data, what the vision is for being able to integrate that into this national framework, what the options are? How data can be added to the 3DHP?
I might, if Sue or Steve want to take that question, I might turn it to them.
Linda, can you repeat the question?
Certainly. I know, well, I thought maybe you might want to elaborate on the idea of a national framework in which local data can be integrated. And if you wanted to maybe address that a little bit about how that might happen
So if you want to mention the types of contracts that involve local stakeholder input, I can take how it fits into the national framework. I can't speak to the contracting details as well.
Right, and I think with respect to data acquisition, once we stand up a BAA, which we hope to do now in FY24, as many of you are well aware, we take applications or proposals for data acquisition that include local funds and then match those funds for data acquisition. With respect to, I guess, local scale data, and Dave can speak more to this, we are working from a specification and the data need to meet the specification. But density maybe is a question, an open question that we need to work through, particularly in the continental US. Dave, did you want to expand on that or?
Yeah, no, that's exactly what I wanted to get on the table with more accurate terms than I was going to be able to muster. How do those local collections hang together in a national framework is that when we bring an elevation drive hydrography local collection from a contract in, the main rivers that flow through that local connection get conflated to this Mainstems network that's already in the views over here on the right. And as many of these Mainstem rivers as possible also get conflated. So we have the same connections from headwater area to outlet area identified with a common identifier. And so especially for things where we're integrating hydrologically relevant features, bridges and stream gauges and things that are impacted by hydrology, we have kind of stability over how those things are linked to the national data set and local data sets, et cetera, all of it. And that becomes the way we work forward by patching in additional data quality or additional data, resolution and quality as we go. Is this conflation of the major components of the network, at least, and as many more of the components of the network as can be given, the geospatial conflation methods that exist and the amount of quality control work that can be done. So that's the scheme, and like Sue was saying, the ultimate resolution can be as fine as we want to extract from the LiDAR, really. And I think there's an expectation that it's a pretty consistent, as fine as the environment represents. We're not leaving anything out. We're going to go as fine as in reality. So.
Kind of on that note, is there any talk of moving away from the scales identification of different data set qualities? It just seems like an antiquated means of differentiating them from kind of a paper map era where
you mean the 100
in and out. Yeah.
You mean the 100K, 24K? Yeah. I don't think the 24K, 12.5K scales are going to be present in this data.
Okay.
The recognition of Slippy map zoom scale numbers, I would imagine might leak into like a generalization filter. But even there, I don't know. That's open for discussion. I would hope we stay away from that for now.
Agreed. Thank you.
And I managed to lose my chat, so let me find it again. There we go. I like this. Okay, is there much difference between the Mainstem concept and GNAS naming? Yes and no. The Mainstem concept supports, well, in most cases, Mainstem is going to follow GNAS name, but not in all. And the reason that we're not in all is we want to have stability as much as possible in these identifiers, so that when data sets are linked together with this identifier, there's not as much need to evolve and update these identifiers. And that's not to say that the GNAS names don't change, but they are a layer of information that we want to allow to change. We want to allow people to update, fix, modify, et cetera, independent of our need to have durable integrations between these data sets. And so that's the argument for not using, say, a GNAS ID. The other argument, or the other difference, is that a GNAS ID is identified, or a name is identified based on whatever colloquial, local, historical reason there was for naming a place or a feature. These Mainstem identifiers are specifically set up for a kind of network backbone ID system that is a hydrologic entity from headwater to outlet. And when set up, ultimately that system has to be a little bit arbitrary, but not arbitrary in a bad way. It's just like you have to choose one, you choose something. So we've used GNIS, we've used arbolet sum, which is the way that NHD uses when there is no GNIS ID to define it. We've used those metrics for what is primary upstream, but now that they're set, and the fact that there's going to be some evolution on top of that is expected. Basically, it's part of the scheme. And so will the EDH part eventually, the goal is that yes, the elevation derived hydrography collections will supersede the NHD geometry, because NHD geometry doesn't necessarily have an elevation component. Sorry, I see Sue answered that question too. And it's because we're trying to add the elevation, the Z component accurately to be integrated with an elevation data product nationally.
Hey, Dave, this is, oh,
Go
sorry.
ahead. No, go ahead, Sue.
You're probably doing it. And Eric from Pennsylvania asked a question that I think you might have missed when you lost your chat about what do conversations about attribute domains look like?
Oh, I see this now. Yeah. So this diagram up here is a good way to talk about that. So in the interest of sustainability and maintainability of the processing, the attributes that we're including in the 3HP production process are minimal and as minimal as possible to support production, and also capture the attributes coming through from the elevation derived hydrography. But an example of a decision we made recently was the attribute for minimum and maximum elevation of a flow line is one that would get added as part of a view. It would not be in 3DHP production as an attribute domain. So just as a guiding principle, right? That's what's guiding the design work is keeping this 3DHP production process lean so we can automate it effectively, reproducibly, make it fast, make it simple, and then add those additional details as needed. And so what's not on this diagram is additional data streams that could come in when we create the views. And that's our opportunity to add things like the visibility filter type attributes for cartography, or add various hydrofabric attributes that are meaningful to the water budget. Things that could come in from the side essentially and get added down the line. So anyways, that's really it's really just the core stuff. Flow line length, drainage area per catchment, key physiographic attributes that we derive along the processing pipelines that are required to generate attributes and the network topology attributes.
All right, any other last questions, comments, suggestions? Dave, do you have any questions for the group?
No, thanks for your time. I'm really happy to have the opportunity to share this work with everybody. And if you have questions, feel free to reach out. My email's available broadly, and first initial last name at usgs.gov. You can find me similar on Twitter and Mastodon and GitHub and all over the place. So very, very, very happy to engage and talk more about this stuff with folks. So.
Well, thank you very much. I've got one more slide for the group. Just want to bring you guys up to date on what we'll be doing next month. If I can find my slide. All right, thank you again, Dave. We appreciate you taking the time. We appreciate you bringing us along on this journey, and NHDPlusHR truly appreciates being a participant in this dialogue. As most of you know, the forum is quarterly, third Wednesday of the month, and next weekend, Sylvia Terziati is going to join us to talk about creating a hydro-enhanced elevation surface using the fully integrated elevation and hydrography 3DHP product. As most of you know, we don't open registration till the beginning of the month. It's a security thing, so please mark your calendars with a placeholder for the third Wednesday of the month, 3 to 4:30 p.m. And unless there's any additional questions or comments, Ben Hickson, if you're still on, can you check the chat? I sent you a message. Truly appreciate you all being here, taking the time today. And again, thank you to Dave, our speaker. And everybody go out and have a great day. Thank you.